All right, so it's my pleasure to introduce our first speaker of this session, Sofiya Yatsyna from Royal Holloway, and she'll be talking about homological finiteness conditions for TDLC groups. Take it away.
So, hi everyone. Thank you for inviting me to give a talk here. Yeah, as Gemma said, I'm giving a talk on the homological finiteness conditions on TDLC groups. And I thought the best place to start actually for most geometric group theorists is so TLC groups are an example of a group called topological groups. So I thought that's probably the best place to start for everyone, just so everyone can have like a basis of what kind of groups I'm looking at. So a topological group, it's just you can consider it just as a group that also acts as a topological space, and it just has that the group operation is continuous and the inversion map is continuous. And here, when we look at the cross product of G by G, we look at using the product topology. So that's just to give everyone some sort of intuition of what sort of groups I'm looking at. And it also, general group theory properties carry through. So if the group is abelian, then the topological group is also abelian. This also works if it's cyclic or nilpotent. And also you can define in a similar way, like topological fields and topological rings. So it's the same kind of idea behind them. So some examples of topological groups that I think we've all seen are the reals equipped with the usual topology. That's usually like the best place to start with it. And then actually subgroups of the reals also. So you have the integers and the rationals, and that's equipped with the subspace topology. And in fact, for any topological group, all subgroups are also topological groups. So it does not just for the reals. And actually, all groups, when you put the discrete topology, are topological groups. So these are just discrete groups. These, I think, the ones that most geometric group theorists work with and love. I kind of work on a larger range where I look at a larger sort of topology around these. And the one that will be the focus of my talk today will be totally disconnected locally compact groups. So what are totally disconnected locally compact groups? So these are totally disconnected locally compact groups. These are groups that have a profinite subgroup in it. So and the subgroup has to be compact open. So some examples of these will be your discrete groups and profinite groups. These are the two trivial examples you work with for TLC groups. But also all sort of subgroups, products, extensions, and direct limits of TLC groups can also be TLC groups. These are known as, like, this class of group is known as elementary groups. You also have non-Archimedean local fields, and generally these can be classed into two groups. So this is the field of p-adic numbers or their finite extensions, or you can have the Formula-1 series over some finite field. And another, I think, interesting example to work with, like if you want to actually have a look and kind of show how the topology works through a TLC group, is actually the automorphism group of a connected locally finite graph. So it's like a nice kind of visual example. I won't show it here, sadly, because I don't think I have the time, but I think it's like a nice exercise for everyone to have a look at. And if you want to like construct and see how the topology, how the topology makes it a totally disconnected locally compact group. I'll also abbreviate totally disconnected locally compact groups to TDLC groups because it's kind of a mouthful. So because these groups are quite large, they're much bigger than your regular discrete groups, we need like a larger group cohomology. And this was initially defined by Ilaria Castellano and Thomas Weigel in 2016. And they defined a rational discrete group cohomology. But in fact, they actually defined this sort of group cohomology for a larger class of groups, not just TLC groups, or groups that they call OS types. So an OS type group is just this topological group where you have an open subgroup that just forms the basis neighborhood of the identity in your group. Now, two simple examples of these can include profinite groups and TDLC groups. So you can just think of them as almost like a generalization of a TLC group almost. Yes. So what do I need to kind of define this like larger group cohomology? So first, let's do with some notation. We have the R is our commutative ring with the unit. We have that RG is the group algebra for any group G. And we have that RG mod is the abelian category of left RG modules. So this is kind of notation I'll be using throughout. And if anyone gets confused or like lost, just like let me know, and then we can go back and I can like work through any examples. I might have also There's also another category I'll go through called RG-dis, and I might have got them confused, but I think I should be okay. So we say that a group is discrete. So this is the discrete part of our cohomology. We say it's discrete if the group action is continuous. So here we have that on the G. So we have that the group has discrete topology, but we have that this product is the product topology. And now if our group G is a discrete group, then this module is just a discrete module. So this is like the regular discrete modules we work with. So what do I do if my actual module is not discrete? So we have this category. This is RG-dis. This is a category of all discrete left modules. And these are objects. This is actually the fourth subcategory of our module RG mod over here. So like this is a fourth submodule of this. And if our module is not discrete, we actually have this functor, which takes this non-discrete module and we apply it, and it takes essentially the largest submodule that is discrete. And another form of discrete is actually smooth. So you can sometimes see like a similar definition, not obviously used for the context of this cohomology, but a similar definition of like this kind of module and this sort of functor, and they usually refer to it to making a smooth module. So what are the nice properties that like this discrete functor actually gives us? So given our group of OS type, it gives us that RG-dis is an abelian category. So that's kind of nice to work with. It also gives us that we have a left exact functor. D also maps injectives to injectives, and it also has enough injectives. This allows us to actually have a minimal injective resolution. So we are able to construct the injective resolutions. And so Castellano and Weigel in their paper in 2016 actually showed that if we look over the rationals, that we also have enough projectives. Hence why we look over rational discrete cohomology when we're talking about TDLC groups, because we want both our modules to have both enough projectives and enough injectives so we can have these resolutions. So how do they define the cohomology? So we take our coefficients from this RG-dis module, and it's defined in very much a similar manner to how we define our regular group, like discrete group cohomology. But we use this D being our discrete functor. So we have that the kth discrete cohomology group is our dx. So they have their own version of like the x functor where you apply the discretization of the functor onto the x functor. And R actually just denotes the trivial left module. So what do we do when this is actually a discrete group? When it's a discrete group over the integers, we actually just get back our ordinary group cohomology. And when we look over a profinite group, we actually get the Galois cohomology of this group. So what do I look at? I would like to also just say before I go into like the silp and spli stuff that I introduced, that I'm taking away a lot of like there are like aspects of my category, not my category, sorry, my rational discrete cohomology that I'm not going to mention here. So this is kind of like a not entirely precise definition of how I'm giving the. So okay, so with this discrete cohomology, we also have something called a bimodule. The bimodule, in fact, just works because we don't have in our category, we don't have our group ring. So in discrete cohomology, we have the group ring and it acts all nice into like it allows us to do nice things with our cohomology. But for our discrete rational discrete cohomology, we don't have that QGs in it. So we create this kind of bimodule. So I don't write the bimodule here, but generally speaking, we need to have this bimodule to allow us to work in this category nicely. But it works essentially like our group ring. So what do I look at? I look at these two invariants called silp and spli. This was defined by Gedrich and Gruenberg over the ring. And it's so silp will be the supremum of projective lengths of injective modules. So that's where we actually get the silp and spli. So we get a spli being the supremum of projective lengths injectives. And similarly, we have it with silp, we have the supremum of injective lengths of projective modules. So where do I look at these with our TDLC groups? So if we have a TDLC group, I've actually shown that if both of the silp and spli are finite, then we have that they are equal. This was also shown over the general group ring and over the ring for discrete cohomology. So this was defined and shown by Gedrich and Gruenberg. A corollary that falls out of this one is that if we have that the global dimension of our over our category is finite, then we also have it's equal to our silp and spli in this group. So what do I work with in these groups? I work with these TLC groups, and I want to show that the main theorem from the paper in Gedrich and Gruenberg that if we have that one is finite, the other one's finite. Now, I haven't been able to show this yet because actually there's a lot of nuances in the proof of this, and we actually need to go past this rational discrete cohomology, and we look at a relative cohomology for these groups. So the relative cohomology for these groups just comes in for like for the final proof of the original paper. But we actually see that in these groups, we want it to be, we might even want to just define it over this relative discrete cohomology as opposed to actually even looking at this rational discrete cohomology. But for now, this is kind of what I've done. And I thank you. I guess this is the end of my talk. I feel like I rushed through. Sorry.
No, you're fine, Sofiya. Let's thank our first speaker. Either virtually or you can unmute. Does anyone have any questions for Sofiya? Well, I'll maybe get the ball rolling. Sorry, you might want to share your slides again. So do you think this conjecture that you have that you've not proven yet? So, like, are you fairly convinced it's true? Like,
yeah, I think it's true, but I think because the area is quite new and this cohomology theory is also quite new, there are a lot of areas that haven't been explored with it. And I think the idea, so initially when I kind of tackled it, I looked exclusively using this cohomology theory and trying to work through there. But the way the original proof works, it goes through into relative cohomology and uses like an item from relative cohomology that holds true, like an equivalent in discrete cohomology. But I don't have that because we don't have relative cohomology here. So I think it is true, but I think it's just we don't have the techniques yet to kind of show this.
okay, cool. And maybe kind of follow up, but I'm probably misunderstanding slash don't know. For pro-finite groups, do you get any of these kind of equalities for silp and spli?
Yes, but I think they're generally trivial. So I think
Okay.
yeah.
Okay. Right.
I can't remember. I think if you look at actual examples, I think profinite groups do hold trivial, but I'll need to double check that one.
Okay, cool. Great. Do we have any further questions in the audience? Feel free to type in the chat if you don't want to unmute. Well. Okay, in that case, let's thank Sofiya again.